Sometimes the really easiest word problems or real life applications are ones like this where they actually give you the equation. So anything that happens in our day-to-day lives that repeats itself on a regular interval can be represented by either a sine or a cosine graph. So one example is tides. Tides come in, tides go out. Tides come in, tides go out. They're periodic that way. And because they follow that schedule, we can make a sine or a cosine equation that models it, and we can figure out what's the depth of the water going to be in 10 hours. What's it going to be in 20 hours? And it's wonderful to be able to use mathematics to figure that out. So here's the equation. The depth of the water is negative 4.5 cos 0.16 pi t plus 13.7. First thing I notice here is the numbers aren't as nice as normal, right? Because when you get to an actual real world problem, the real world doesn't be like, oh, you don't like decimals? I'm sorry. We'll make the number nice for you. No, the real world doesn't do that. Usually those questions are a lot messier. So we want to sketch this graph, and we're going to do the same technique we were doing yesterday. We're going to look at each of these things, and again, I do a little bit of thinking on both the D and the A before I draw my grid. So I drew my grid there, but before I did that, I was like, my D value is 13.7. That's my center line, and my amplitude is 4.5. So I'm not going to go into the negatives. So what I can do here is I'm going to pick somewhere, I'm going to say that's 13.7. And that sort of sets my scale up, and I can draw a dotted line along here. Y equals 13.7. And then I use my amplitude, so that's all for D. I use my amplitude to find my maximum and my minimum. So I'm going to mark, according to this, that should be about 4.5 and 4.5. If I go down 4.5, I will get to 9.2. If I go up 4.5, I will get to 18.2. And that's all that's needed for your amplitude. Your period is 2 pi over your B value. So I'm just going to extend it here. I'm going to write that down here. My period should equal 2 pi divided by, and this of course would be a calculator question because I don't know if you can do 2 divided by 0.16 in your head. And we get 12.5. And you could probably do the pi's canceling, and then you just have to do 2 divided by 0.16. So we get 12.5. So I'm going to mark somewhere along here 12.5 and divide it into 4 equal sections. Well, half of 12.5 is 6.25. Half of that would be 3.125. And 3 of those would be 9.375. We divide it into 4 equal sections with 1 period. There is no C value. So technically in this one, we don't have to do these 2 things. Do you see that there's going to be no shift? What you would draw normally as your dotted line without the shift is going to be your final graph. So I'm going to go to my final graph. This is a negative cos graph. Cos graphs normally start at a maximum. A negative cos graph would have a vertical reflection and start at the minimum. And then you can go minimum, center line, maximum, center line, minimum. Wow, my dots. And we draw our curve nicely through those points. And we sketch the graph. Perfect. Okay. Then part B here says a big ship So this is a big boat, a big ship. And because it's so big, it needs a certain depth of water in order to be in the dock safely. It needs 14.5 meters of water to be in there safely. On our graph, we can go here, I'm going to label it in blue because it's water level. I'm going to label 14.5. I'm going to draw that wave across here. Can you see that only from this point to this point, in that section, the water is deeper than 14.5? So we're going to look at how, since this is a calculator question, how you could use a graphing calculator. And this would be very important if you're taking AP next year in applying this and figuring this out. So what we're going to do is we're going to draw this graph. We're going to learn how to use our calculator to do that. So if you have a graphing calculator, you can take yours out. If not, you can just watch along. I'm going to open up my calculator here. First thing I'm going to do is I'm going to go to y equals, and I'm going to type in my equation. Negative 4.5 cos 0.16 pi, and then the x button is right here beside the alpha button. Notice my calculator is already in radians. That's important. And then plus 13.7. Now, most likely, if I go to hit graph right now, let me just check. Yeah, I don't see very much. Because if you have a graphing calculator, normally your graphing calculator is set to see between negative 10 and 10 and negative 10 and 10. Let me just go back to my graph here on our equation. Let me click here. Okay? And right now, this is what my calculator sees. It sees up to 10, down to minus 10, up to 10 this way. The purple box is what I'm looking at on my calculator. Can you see that that's not very helpful right now? I would like to see the actual graph. So now we're going to look at how do I take this window that I'm looking at in my calculator and move it so I can see the actual graph. And on your calculator, there is, right here at the top, a window button. That changes what you can see. So if I click on that window button, you can see right now the x's go from minus 10 to 10, and my y's go from minus 10 to 10. What would I like to see? Well, my x's, I don't need to go back to minus 10. Sometimes I like just a minus 1 so I can still see my y-axis. And my period was 12.5, so maybe I'll go up to 15. A little bit more. Okay? You've got some freedom here, because if your window's bigger than mine or a little bit smaller, as long as you can see what you want to see, you'll be fine. Same thing with my y-min. I'm just going to leave a minus 1 there for now, just so I can see my x-axis. But then my maximum was at 18.2. So if I go up to 20, that should be enough. Some other things you can do that are kind of interesting here. You can set your scale. You know how I had my ticky marks at 3.125 for each of them? I can actually change that to 3.125. And now when I graph, it actually has the ticky marks exactly the same as I drew them on my graph. On the y, not so much. It's just going by ones right now. I could make my y's go by 5s and have less of them. 5, 10, 15, 20. But now we can see our graph. And the graphing calculator can solve these questions very, very efficiently and very, very quickly. So what we can do on the graphing calculator, and you can do this on Desmos, an online graphing calculator program as well. In Y2, I'm going to draw the horizontal line at 14.5. That draws that 14.5 line straight across. And we already talked about that in between here and here. That's when the water is deep enough for that big ship. So if I can find out where these two graphs intersect, I'll be able to solve this problem. Anything you want to calculate with your graphs is above the trace button. Here it says calculate. That's for calculating anything on your graph. So if I go second and then I hit calculate, I can find values, I can find x-intercepts or zeros, minimums, maximums, and I can also, here number 5, find where two graphs intersect. So I'm going to push enter on that. It's automatically going to be on one curve. It says, do you want this to be your first curve? Yes. And the reason I ask that is you could be doing something complicated with like 5 graphs, and you want to find out where 2 of them intersect, so then you have to select which one. When we only have 2, this is going to be really easy. First curve, yep. Second curve, yep. Guess, do I think it's going to be this one or this one? Well, it'll always find the closest one. So I'm pretty sure it's going to find the one to the right. Push enter on guess. And it's a 9.019. So I can go back to my graph here. And I would know straight down from this blue point to 3 decimal places, 9.019. If I want to find the other one, straight down from this one, well, I'd have to go back to my calculator, do the same thing. I want to calculate number 5 where they intersect, but this time I have to use my cursor, and I have to move my cursor closer to the first one. Push enter once, enter twice, guess, push enter again. 3.481. And so from the time 3.481 to 9.019, it is safe, and we can go and answer this question. There we go. Oh, I don't have the answer here. Oh, maybe I do. No. I figured it out. I'll just write it down. So for part B, I take 9.019 minus 3.481. What is that going to be? 9.019 minus 3.481. 5.538. And if you had this question in AP Calculus, and it was a calculator question, they would expect you to use your calculator because it is way, way faster than algebraic. Okay? Now, they won't ask on your provincial exam one this complicated without a calculator. Okay? This is more important for AP Calculus moving forward. I will show you, because once you go to university, you'd be expected to know how to do this, and you have the information already to be able to do this using our cast rule, reference angles, angles in standard position. And I will show you this. It'll be in the video, but I do not expect you to write this down because I'll go too fast and you won't be able to have time to write it down. So if you want to write it down for yourself later, you can rewatch the video. But I'm also going to show you how you would solve this, part B, algebraically, without a graphing calculator. So first of all, you were told that the depth was 14.5. So that means we could substitute in the 14.5 where the y is or where the d of t is. And now you have to solve for t. And that t is inside of cos. So the first thing I'm going to do is I'm going to rearrange my equation to just get my cos by itself. Because then you can use your cast rule, reference angles, and things to solve. So you would move the 13.7 over, divide by negative 4.5, and that gets your cos by itself. Now, when we solved equations, usually they were easier, and what was here? Just theta, right? And then you could do cos inverse to find your reference angle, and then cos is negative, so you would look in quadrants 2 and quadrants 3 and find your answers. But we don't have a nice theta here. We have this ugly 0.16 pi t. So there's a beautiful thing you can do in mathematics. If you have something ugly you don't want for a while, you just say, I want it to go away. So why don't I just say theta is equal to that for the meantime? Because if I say theta is equal to what's in this green box, then my question looks like regular grade 11 and grade 12 math. How do I solve this? Well, I find my reference angle by doing cos inverse of the positive. Becomes 1.392. And then I find my answer in quadrant 2, and I find my answer in quadrant 3. Nice. But those are answers for theta. Theta is equal to 1.749, and theta is equal to 4.533. But what did theta equal? I temporarily substituted theta for that 0.16 pi t. And now I can substitute back. So if I substitute back, how do you get t by itself? You divide by 0.16 pi, and we get our 3.48 in quadrant 2. We do the same thing, and we get our 9.02 in quadrant 3, which are the two answers that we found with our graphing calculator as well. So this is what would be expected in university, because it just uses the stuff that you've done so far. But what's new in this one is that little substitution, right? That if something's not nice, substitute it out temporarily, then substitute it back afterwards. And that can help us solve. Okay, we're going to do a couple more word problems of other things that repeat themselves. How many people have been on a Ferris wheel at the X or at different places? Right? So this question is a little bit more difficult than the first one, because the first one they gave you an equation. This one, they just give you a situation. And from the situation, we should be able to draw the graph. And from the graph, we can use DAB-C to find an equation. So that's what's going to happen. What I'm going to do here is I am going to draw a Ferris wheel so you can picture it. Oh, it's got nice fancy blue chairs. Beautiful. There we go. And there's a super happy person who is there we go. There's our super happy person going on our Ferris wheel. And they're going to get on the ride and travel around. Yay! Oh. And back again. So this is the situation. They tell us, here's our Ferris wheel. It has a radius of 15 meters. It takes 20 seconds to go all the way around like this. Oops. Back on the chair. And they start at the bottom, right? It'd be very scary if they had a mechanism where it's saying, sorry, this Ferris wheel, you have to start at the top. So just put you in this catapult and just try to jump on the top as possible. No, you get on at the bottom. So right beside this Ferris wheel, I'm going to draw, trying to make it accurate. You see my maximum is way up here. Minimum is just off the ground. Ferris wheels that go into the ground are quite dangerous. Would not be good. And this is where you're starting. So I know that that is where I'm starting. How high is that? Get 1 meter above the ground. So I know this is at 1 meter. How high above the ground is the person when they're way up here? What's our maximum going to be? The question tells us. Let's read it again. Ferris wheel has a radius of 15 meters. So the radius, what does that mean? That means from the center out to the edge is 15 meters, which would be in any direction out to the edge, right? Can you see your diameter is 30 meters? And if you're 1 meter when you start, the maximum height you will get is 31. 30 meters higher. And halfway in between, you'll be at 16. Well, that'll be your center line. So we've already figured out our D value. In fact, we've also figured out our A value, that our amplitude has to be 15. But we'll get to that when we get the equation. We want to just draw one graph of this. What time will you be at the top? Okay? Careful, it rotates once every 20 seconds. That means all the way around is 20 seconds. How long will it take you to get to the top? 10 seconds. So we can go here and we can mark 10 seconds and we would say, I know at 10 seconds I'm right at the top, and I would know at 20 seconds I would be back at the bottom. In fact, your 20 seconds is one full period. So we can divide this into 4 equal sections, which would include 5 and 15, which means you start at the bottom. At 5 seconds you'd be halfway, at 10 you'd be at the top, at 15 you'd be back halfway. And depending on how many times you go around, this is what your graph would look like. So we graph this one, and then it says find its equation. So to find its equation, we can think about find its equation. We can think about dab C. And like I said, we already figured out that your D value was 16. Your A value is 15. We know that our period equals 20, and our B value is always 2 pi over our period. So our B value is going to be 2 pi over 20, and I actually really like leaving it that way. I know you could reduce it to pi over 10, and most of the multiple choice questions on your take-home quiz reduce them. But if I leave it as 2 pi over 20, what I really like about this is I see the period in my formula. I see the 20 on the bottom, and I know that that's my period. And so now that you've got the D, the A, and the B, which doesn't change, the C is going to be dependent on where you start. And we have multiple options. So if I wanted to make, and I'll start with my favorite option. My favorite option on this one is a cosine graph that starts at the minimum. Do you see, and I'll do these all in different colors, picking the point. If I pick this purple point, starting at the bottom, you see that that has no shift. That makes it, in my opinion, the easiest graph to write. So I can go y equals, I know my A value is 15. It's going to be a negative 15. I'll make that even more obvious. Y equals negative 15, because I'm doing a negative cos graph starting at the minimum. My B value is 2 pi over 20. X, no shift, and my D value is still plus 16. Next, I'm going to pick this green point. that green point is in the middle, going up. Should I use sine or cosine for that? Middle going up would be sine. So middle going up would be a positive sign. So 15 sine 2 pi over 20. The plus 16 is there. But now I have shifted, that green point is shifted 5 units to the right. X's are liars. So that would show up as a minus 5 inside. And notice that I write it in factored form. Orange. I could pick this maximum. If I started at a maximum, that would be a cosgraph, a positive cosgraph. So notice again, my A, my B, and my D values do not change, sine or cosine. Your amplitude is the same for both of them. Your center line is the same for both of them. Your period is the same for both of them. The only thing that changes is where you start. And that orange point, do you see that orange point? That would have been shifted 10 to the right, that maximum. So how do I show a shift of 10 to the right? X minus 10. And we could keep going. I could find the next point, make a different color, do a new shift. I could make a negative, right? If I used 15, this blue point right here, now it's going down. That would be a negative sine graph if I shifted 15 to the right. Okay? So we can use any one of these. So I'm going to take this, I'm going to put it in my graphing calculator, because I'm going to answer the next two questions with the graphing calculator just to get used to it. So I'll pull out my graphing calculator and clear out these equations. And I'm going to use the negative 15 cos (2 pi over 10) x, the one that had no translation, plus 16. And I'm going to go to my window, and since it took 20 seconds to go around, I'm going to go past 20. Maybe I'll go up to 25. My scale for x's, I'm going to go by 5s. My maximum was at 31, so maybe I'll go up to 35. I want to hit graph. Do I see my, oh yeah. How far did I go up? Oh, I made a typo here. It's like, it doesn't look like what I wanted. 2 pi over 20. There we go. Very similar to the graph that we just had. Now our second question's here. Estimate the height after 22 seconds. Now it's estimate, so that means this could be a non-calculator question where you just take your graph, you go to 22, you put it up here, and you go across and just make an estimate. I don't know, 5, 6, 4? Those are all estimates. That would be perfectly fine. If we wanted to find it exactly, we can use our graphing calculator. And the way that we would use our graphing calculator is, again, we go to second calculate. Well, what are we interested in? A certain value. So I push 1. Well, what would you like x to be, it asks. Well, I wanted x to be 22 seconds. So I push enter, and it's 3.864. We were pretty close when we said 4. Not as close when we said 5. Not as close when we said 6. But, you know, it was an estimate. So we can use our graphing calculator to plug in any value you want and find the time. So on this, estimate the height, 3.864. These are word problems. You need to have units. If we don't have units in our answer, we will lose an E5 error for missing units. Estimate at what time you will be 20 meters above the ground. So again, back to my calculator. If I want to find a certain y value, I have to go to y equals, and in a second equation, type in 20. And that draws the horizontal line at 20. And now I can go second, calculate. Where do these intersect? enter, enter, enter. One's at 14.14. 3 decimal places, 14.4141. And units would be seconds. If I say this is approximately 14 seconds, okay? So here was 20. 20, I'll draw a green line for 20. And we're saying that this point is approximately 14 seconds. Without a calculator, can you tell me what that is approximately? How can we use what we know about sine and cosine graphs to do this without a calculator? There's a lot of symmetry in sine and cosine graphs. That's why your reference angles work. That's why you have the cast rule and stuff like that. Can you see from 10 seconds here that it's symmetrical on both sides? So if this was approximately 4 seconds that way, approximately 4 seconds that way would be at about 6. And we could take the decimal 141 into account and find it perfectly. But that's what it's going to be really close to.
Alex Simonson to the office, please. Alex Simonson to the office.
If I want to take a word problem and minimize it to give you the least amount of information possible and still have you be able to do the question, all you need is 2 points, one max and the next min, or one max and the next max, or one min and the next min. Then you can find everything on the graph. So this is this question here, again, a tides question with the least amount of information possible. And also, it's real life, it's going to be a little bit messy because it's dealing with time. And there's only 62 minutes in the hour. So unfortunately, I can't write 1042 as 10.42. Can you see that 1030 would be like 10.5, half an hour? We have to figure out how to work with 42 minutes as well. So we're going to draw a picture of what we know so far. Graphs are wonderful for visualizing what you know. The world's highest tides occur at the Bay of Fundy, periodic in nature. The maximum depth of the water is 8 meters at 4:30 a.m. So I feel pretty confident. I'm going to put 4.5 for 4:30, and I'm going to put 8 up here. And I'm going to draw that dot. That's one piece of information that I know. 6 hours and 12 minutes later, so this is 4.5 hours. 6 hours would be a little bit, that looks like about a good approximation of 6 hours and a bit. It's going to be at 2. Well, I'm pretty confident I can label 2. But now I need to write, my calculator doesn't let me do minutes. I'm going to need to do 10 point something. How do you change 42 minutes to a decimal? 30 minutes is 0.5. 15 minutes would be 0.25. 42, how would you figure that out? It's 10 point something. How do I know 30 minutes is 0.5?
30 is half of 60.
30 is half of 60, right? In fact, you could write 30 over 60, well, that's the same as a half, that's 0.5. Could we use the same idea with 42? Absolutely.
42 over 60.
42 divided by 60. Okay. Can you reduce that? Can you divide them? Oh, look at this. They do both divide by 6. And I'm pretty sure you can change 7/10 to a decimal pretty easy. 0.7. So this will be a 10.7, which makes this distance between here and here 6.2. What's the period of my graph? Not 6.2. Because period goes from minimum to minimum, maximum to maximum, middle going up to middle going up. I've only got maximum to minimum. How long is it going to take to get back to the next maximum? Another 6.2. So if I add another, this will be 16.9. 6.2 times 6.2, my period is going to be 12.4. And I could cut these in half, and then I have my 4 sections. Do you see that your middle line is going to be at 5? And at this section it would be at the middle, at this section it would be at the middle, and we have enough information to get our graph. And then we want to find the equation. It says one equation with sine, one equation with cosine. So I'm going to go dab C. And again, the D value center line, that's 5. The A value up to 8 down to 2 is 3 units. The period was 12.4, so your B value will be 2 pi divided by 12.4. And the dash C we never write because that's going to change depending on which graph that you're going to use. Let's say you want to use a sine graph. The sine graph starts in the middle going up. So pick a middle point going up. There's actually 2 possibilities here. You could choose either one of those. Half of 6.2 is 3.1. So I would know that this is at 7.6 and this is at 13.8. I might use that 13.8 value. Amplitude is 3. Sine. Period is 2 pi over 12.4. X minus 13.8 plus 5. For cos, go to purple. I'm going to pick a maximum. Amplitude is still 3. V value is still 2 pi over 12.4. X minus, now my maximum is shifted 4.5 to the right, so I put a 4.5 in, plus 5. $130 would be 13.5. If I go up from 13.5 and over, I could estimate that at about 4. We could use our graphing calculator to find it. But I'm going to end the video there and give you some time to start your take-home quiz.